Geophysics is a fascinating field that explores the physical properties and processes of the Earth using principles of physics. It delves into the study of the Earth's interior, its magnetic and gravitational fields, seismic activity, and more. One interesting fact about geophysics is that it is a highly interdisciplinary science, drawing on knowledge from physics, mathematics, chemistry, and geology to understand the Earth's complex systems. Geophysicists use a variety of methods to investigate the Earth's structure and dynamics, including seismic surveys, gravity measurements, magnetic surveys, and electrical resistivity surveys. These methods provide valuable insights into the composition, temperature, and movement of the Earth's layers. Geophysics plays a crucial role in understanding natural hazards such as earthquakes, volcanic eruptions, and landslides. By studying the Earth's subsurface, geophysicists can help predict and mitigate the impact of these events, saving lives and property. Geophysics also plays a key role in resource exploration, including the discovery of oil, gas, minerals, and groundwater. For example, seismic surveys are commonly used in the oil and gas industry to locate underground reservoirs. In addition, geophysical methods are used in environmental studies to monitor groundwater contamination, assess soil stability, and study climate change. Geophysics is a rapidly evolving field, with new technologies and techniques constantly being developed. One interesting statistic is that the global geophysical services market was valued at over $16 billion in 2020 and is projected to grow significantly in the coming years. As our understanding of the Earth's processes deepens, the applications of geophysics will continue to expand, offering new insights into our planet and its resources. Geophysics is truly a dynamic and vital science that contributes to our knowledge of the Earth and its environment. The history of geophysics is a rich tapestry of scientific discovery and innovation that spans centuries. One of the earliest recorded instances of geophysical observations dates back to ancient Greece, where philosophers such as Thales of Miletus speculated about the nature of the Earth and its composition. However, it was not until the 19th century that geophysics began to emerge as a distinct scientific discipline. In 1831, Michael Faraday's discovery of electromagnetic induction laid the groundwork for the study of Earth's magnetic field, a key component of geophysics. Another milestone in the history of geophysics was the development of seismology in the late 19th century. The devastating Lisbon earthquake of 1755 sparked interest in understanding seismic waves and led to the establishment of the first seismological observatories. The early 20th century saw rapid advancements in geophysical exploration, with the invention of new instruments such as gravimeters, magnetometers, and seismographs. These tools revolutionized our ability to study the Earth's interior and paved the way for modern geophysics. One interesting fact is that the International Geophysical Year, IGY, in 1957 to 1958 marked a significant milestone in the history of geophysics. During this collaborative effort involving 67 countries, scientists conducted groundbreaking research in various geophysical disciplines, leading to major discoveries such as the existence of the Van Allen radiation belts. Today, geophysics continues to evolve with the advent of cutting-edge technologies such as satellite-based remote sensing and advanced computational modeling. The field has grown exponentially over the years, with over 20,000 geophysicists estimated to be working worldwide. As we look to the future, the history of geophysics serves as a testament to human curiosity and ingenuity in unraveling the mysteries of the Earth. Geophysics encompasses several branches, each focusing on different aspects of the Earth's physical properties and processes. One of the key branches is seismology, which studies seismic waves generated by earthquakes and other sources to understand the Earth's internal structure. Seismologists use networks of seismometers to detect and analyze these waves, providing valuable insights into the composition and dynamics of the Earth's layers. Another important branch is geomagnetism, which investigates the Earth's magnetic field and its variations. Geomagnetic studies have revealed the existence of magnetic anomalies and helped map the Earth's magnetic field, crucial for navigation and understanding the planet's geodynamo. Geodesy is another branch of geophysics that focuses on measuring the Earth's shape, rotation, and gravitational field. Geodetic techniques such as GPS have revolutionized our ability to precisely determine positions on Earth's surface and monitor tectonic movements. A lesser-known branch is aeronomy, which explores the Earth's upper atmosphere and its interactions with the Sun. Aeronomers study phenomena like auroras, ionospheric disturbances, and space weather, shedding light on the complex dynamics of our planet's outermost layers. Interesting fact: the field of exploration geophysics, which applies geophysical methods to locate subsurface resources like oil, gas, and minerals, is a significant branch with practical applications. Exploration geophysicists use techniques such as seismic reflection, gravity surveys, and electromagnetic methods to image subsurface structures and identify potential resource deposits. In the United States alone, the geophysical services industry generated over $2.5 billion in revenue in 2020, highlighting the economic importance of exploration geophysics. Environmental geophysics is another branch that focuses on studying the Earth's near-surface environment and its interactions with human activities. Environmental geophysicists use methods like ground-penetrating radar and electrical resistivity surveys to assess soil contamination, monitor groundwater resources, and investigate archaeological sites. The field of planetary geophysics extends the principles of geophysics to other celestial bodies in our solar system and beyond. Planetary geophysicists study the interiors, surfaces, and atmospheres of planets, moons, and asteroids using data from spacecraft missions and telescopic observations. With ongoing advancements in technology and data analysis, the field of geophysics continues to expand its branches and push the boundaries of our understanding of the Earth and beyond. Geophysics employs a wide range of methods to investigate the Earth's subsurface and physical properties. One of the most widely used techniques is seismic reflection, which involves sending sound waves into the ground and recording the reflections to create images of underground structures. Seismic reflection surveys have been instrumental in mapping sedimentary basins, fault lines, and reservoirs for oil and gas exploration. Interestingly, the deepest seismic reflection profile ever recorded was in the Mariana Trench, reaching depths of over 11 kilometers. Another important method in geophysics is gravity surveys, which measure variations in the Earth's gravitational field to map subsurface density variations. Gravity surveys have been used to discover mineral deposits, map tectonic structures, and even detect underground caves. In fact, the highest gravity anomaly ever recorded on Earth is located in the Hudson Bay region of Canada, with gravity values exceeding the global average by over 100 milligaules. Electromagnetic methods are also commonly employed in geophysics to study the Earth's electrical conductivity and detect subsurface features. Ground-penetrating radar, a type of electromagnetic survey, uses high-frequency radio waves to image shallow subsurface structures with high resolution. Notably, ground-penetrating radar has been used in archaeological studies to uncover hidden artifacts and structures without excavation. Another fascinating method in geophysics is magnetotellurics, which measures natural variations in the Earth's magnetic and electric fields to image subsurface resistivity structures. Magnetotelluric surveys have been instrumental in studying the Earth's crust and upper mantle, providing insights into volcanic processes and tectonic plate movements. It is estimated that over 50,000 magnetotelluric stations are currently operating worldwide, contributing to ongoing research in geophysics. Remote sensing techniques, such as satellite imagery and airborne surveys, play a crucial role in monitoring environmental changes, mapping land use, and studying natural disasters. The European Space Agency's Sentinel satellites, for example, provide valuable data for monitoring deforestation, urban expansion, and sea level rise. With the advent of advanced technologies and data analytics, geophysicists continue to innovate and develop new methods for exploring the Earth's complex systems. Earth science encompasses a wide range of disciplines that study the Earth's physical, chemical, and biological processes. Geophysics plays a crucial role in Earth science by providing valuable insights into the planet's structure and dynamics. One fascinating application of geophysics in Earth science is the study of plate tectonics. Geophysicists use seismic data to map the movement of tectonic plates and understand the processes driving earthquakes, volcanic eruptions, and mountain formation. It is estimated that the Earth's tectonic plates move at an average rate of about 2 to 10 centimeters per year, highlighting the dynamic nature of our planet's crust. Another intriguing application of geophysics in earth science is the study of paleomagnetism. By analyzing the magnetic properties of rocks, geophysicists can reconstruct the Earth's past magnetic field and track the movement of continents over millions of years. One remarkable fact is that the theory of plate tectonics, supported by geophysical evidence, revolutionized our understanding of Earth's geological history and continues to shape research in earth science. Geophysical methods are also used to study the Earth's water cycle and climate systems. For example, satellite-based remote sensing techniques measure changes in sea surface temperature, ocean currents, and ice cover to monitor climate patterns and predict extreme weather events. The Gravity Recovery and Climate Experiment (GRACE) mission, launched in 2002, provided unprecedented data on global water distribution and ice melt, contributing to our understanding of climate change. In addition, geophysical surveys are used to study the Earth's interior composition and thermal structure. Seismologists analyze seismic waves to infer the properties of the Earth's mantle and core, revealing insights into the planet's heat flow and mineral distribution. It is estimated that the Earth's core temperature exceeds 5,000 degrees Celsius, maintaining the planet's magnetic field and driving geological processes. Geophysical methods are also applied in geothermal energy exploration, where heat from the Earth's interior is harnessed to generate electricity. Geothermal power plants use techniques such as seismic imaging and temperature measurements to locate hot subsurface reservoirs and extract steam for energy production. The global geothermal power capacity reached over 14 gigawatts in 2020, with countries like the United States, Indonesia, and the Philippines leading in geothermal energy production. Overall, geophysics plays a vital role in advancing our understanding of earth science and addressing key challenges related to natural hazards, climate change, and energy sustainability. Natural resource exploration is a key application of geophysics, with methods such as seismic surveys and electromagnetic techniques playing a crucial role in locating subsurface deposits. One interesting aspect of resource exploration is the use of airborne geophysical surveys, where aircraft equipped with sensors map the Earth's surface to identify mineral and hydrocarbon potential. These surveys cover vast areas efficiently, providing valuable data for mining and oil exploration companies. In fact, the global geophysical services market for mineral exploration was valued at over $2 billion in 2020, with a projected growth rate of 6% annually. Another fascinating application is the use of satellite-based remote sensing for monitoring vegetation health and identifying potential mineral deposits. Remote sensing data can detect subtle changes in vegetation patterns that may indicate underlying mineralization, helping target exploration efforts more effectively. Notably, the Landsat program, launched in 1972, has provided over 4 decades of continuous Earth observation data, supporting resource exploration and environmental monitoring worldwide. Geophysical methods are also employed in groundwater exploration, where techniques like electrical resistivity surveys and ground-penetrating radar help map aquifer structures and assess water quality. Groundwater is a vital resource for agriculture, industry, and human consumption, with over 2 billion people worldwide relying on groundwater as their primary water source. Geophysical surveys have been instrumental in locating and managing groundwater resources sustainably, ensuring water security for communities around the globe. Geophysical methods play a crucial role in environmental studies, providing valuable insights into the Earth's near-surface processes and resources. One interesting application is the use of ground-penetrating radar, GPR, to assess soil contamination and monitor underground structures. GPR uses high-frequency electromagnetic waves to image subsurface features with high resolution, making it a powerful tool for environmental investigations. In fact, GPR has been used to detect buried archaeological sites, underground storage tanks, and even unexploded ordnance, helping mitigate environmental risks and preserve cultural heritage. Another fascinating application of geophysics in environmental studies is the monitoring of land subsidence using satellite-based interferometric synthetic aperture radar, INSAR. INSAR technology measures ground deformation with millimeter-scale precision, allowing scientists to track changes in land elevation over time. Notably, INSAR data has revealed significant subsidence rates in regions like the San Joaquin Valley in California, where groundwater extraction has led to land sinking at rates exceeding 25 centimeters per year. Geophysical surveys are also used to study coastal erosion and sediment transport, providing critical information for coastal management and climate adaptation strategies. For example, marine seismic surveys can map underwater sediment layers and identify erosion hotspots along coastlines, helping protect vulnerable ecosystems and infrastructure. The global geophysical services market for environmental studies was valued at over $3 billion in 2020, with a projected growth rate of 5% annually. This highlights the increasing demand for geophysical solutions in addressing environmental challenges and promoting sustainable resource management. As geophysical technologies continue to advance, they will play a key role in monitoring environmental changes, assessing natural hazards, and supporting conservation efforts worldwide. One of the key challenges facing geophysics is the need for continuous innovation and technological advancement to address complex earth science questions. With the increasing demand for sustainable resource management and environmental monitoring, geophysicists are exploring new methods and tools to enhance their capabilities. For example, the development of autonomous underwater vehicles, AUVs, equipped with geophysical sensors allows for high-resolution mapping of the seafloor and underwater structures, revolutionizing marine geophysics research. In addition, the integration of artificial intelligence and machine learning algorithms into geophysical data analysis is transforming how we interpret and model Earth processes. These advanced computational techniques enable geophysicists to extract valuable insights from large data sets and improve the accuracy of subsurface imaging. The future of geophysics also holds exciting prospects in planetary exploration and space science. Geophysicists are actively involved in missions to study other celestial bodies, such as Mars, the Moon, and asteroids, using geophysical methods to unravel their geological history and composition. Notably, NASA's InSight mission to Mars, equipped with seismometers and heat flow probes, has provided unprecedented data on the red planet's interior structure and seismic activity. The global geophysical services market is projected to reach a value of over $20 billion by 2030, driven by increasing investments in natural resource exploration, environmental monitoring, and infrastructure development. Geophysics is poised to play a critical role in addressing global challenges such as climate change, natural hazards, and sustainable energy production. By pushing the boundaries of scientific discovery and technological innovation, geophysicists are shaping a more informed and resilient future for our planet. The field of geophysics continues to evolve, with over 50,000 magnetotelluric stations operating worldwide. The global geophysical services market was valued at over $16 billion in 2020 and is projected to grow significantly. In the United States alone, the geophysical services industry generated over $2.5 billion in revenue in 2020. The Landsat program, launched in 1972, has provided over 4 decades of continuous Earth observation data, supporting resource exploration and environmental monitoring worldwide. Geophysicists are actively involved in missions to study other celestial bodies, such as Mars, the Moon, and asteroids, using geophysical methods to unravel their geological history and composition. The global geophysical services market is projected to reach a value of over $20 billion by 2030, driven by increasing investments in natural resource exploration, environmental monitoring, and infrastructure development.